То есть на чем основывается утверждение, что это сойдется?
Смотри, если у тебя, как в части конкурса, это не сойдет, значит, ты представишь, почему это не сошлось. Очень просто.
А в результате у нас, ну, как результат, если представить, что это имплементировано, у нас что достигается? Быстрее блок propagation происходит?
Во-первых, достигается повышенная безопасность за счет того, что появляется verifier. Во-вторых, ну, собственно, повышенная она становится ультимативно повышенной, достаточно. С verifier. Без verifier нет, это можно доказать. Значит, кроме того, да, block propagation, то есть finality, можно достичь быстрее с помощью этого механизма. Потому что на самом деле мы пересылаем блок, если как бы если нарисовать схему мысленную, то как бы блок... сейчас мне тут пишут еще 20 чатах. И всем что-то надо, извините. Короче говоря, то, значит, мы посылаем блок кандидата, рассылаем. Вместо сейчас в сети рассылается блок уже после того, как консенсус, все фазы консенсуса закончены. Да? Блок уже финальный с точки зрения треда рассылается по сети. Естественно, таким образом мы ждем финальности как бы треда, потом мы посылаем это все по сети, оно доходит до мастера и записывается туда, и все. Значит, ну, в этом процессе проблема в том, что мы ждем 66% подписи треда, а потом мы ждем еще консенсуса мастера на это. Здесь идея в том, что мы рассылаем блок кандидат, не ждем никакого консенсуса нигде, мы рассылаем блок кандидат, и этот блок кандидат уже верифицируется верифайером, поскольку я там, кстати, забыл отметить, сейчас я еще отмечу один момент. Да, жирненьким я там выделяю важные вещи. Я еще пройдусь, там забыл важный момент отметить жирненьким, на который надо обратить внимание. Значит, поскольку ну, атака на верифайера, в принципе, теоретически, ну, очень маловероятна, то ну, это как раз доказано уже. То, в принципе, на моменте, когда схема верификации, ну, схема верификации имеет две части. Одна часть – это, собственно, верификация блока, вторая часть – это бродкаст, доказательство бродкаста. Если мы доказываем, что бродкаст вообще произошел, да, что он не был выборочным, то есть он был разослан всем, 51% всех нод, и после этого у нас есть verifier, то как бы, ну, probability of attack, он очень низкий, в white paper написано цифра. Вот, это ниже, чем биткоин, ну, probability атаки после 6 блоков. Вот, и поэтому, как бы на самом деле, мы можем снизить threshold BFT. А кто может сказать мне вот на звонке сейчас, зачем вообще оставлять BFT?
Аргумент, по-моему, не очень. Кто на звонке может сказать. Математики, наверное, эти могут сказать.
Нет, это не математики дело. Зачем нужно оставлять BFT в этой схеме вообще? Ну, никто не думал.
By the way, we have some English-speaking people here, so if you don't mind, let's switch to English,
I can
please.
switch to English, yeah.
Hello everyone, and thank you.
Hi, Stefan.
Switch in English.
Bonjour, comment ça va? Tout est bien? On peut parler français.
Très bien, merci beaucoup.
Ouais, mais je pense que les autres, поэтому c'est difficulté pour comprendre. Okay, we switch to English then. Anyway.
Thank you very much.
So the probability of the attack after the verifier and the broadcast protection is implemented is such low number that in fact, like, we can finalize right here. Again, in fact, we can finalize. It's like a Solana in a way, but better, because we can finalize once the block is out, because the collator will never try to cheat, because his like his probability of losing the stake is close to 1. It's like really close to 1. So in that respect, there are the probabilistic finality is achieved once you have this tool, right? And that's important because if you have a single transaction on the network, right, not a chain of transactions, but a single transaction, you can finalize right here. Like if you can have a node which listens to the broadcast protection, and once the node has the proof that the broadcast has been well performed, then they can finalize this block immediately, like transaction immediately, more or less. The only problem is the forks, like what happens if the block is not then validated, really. It's just, and then there is another candidate, and that other candidate may not have the transaction. So in terms of finality, that's why we need RAMP as a second part, which is not here, not yet. I mean, which is second contest. Because it's much more. Actually, this one is it's simpler than RAMP, actually. This part is, despite the fact that this is a core of consensus, it is actually simpler than RAMP. RAMP is more complicated than anything we've done before. Like any other part of the node you take, the BFT consensus, anything, RAMP is more complicated than that. So RAMP ensures that your message is delivered to the block in the same order. Let's received. Again, it's also probabilistic, but again, the RAMP is the second part because, like, okay, so if the second candidate has been collected and this candidate did not include your transaction, then kind of you couldn't finalize on the first attempt, right? But if you have a probabilistic, like very high probability that your transaction will be included in all the blocks that has been collated on the same height, then kind of you have a probabilistic finality when you have the first broadcast message, broadcast protection, right? But so this is just, no, I just explained because Ivan asked the question, what we achieve with this protocol. So we achieve security, that's first thing, and that's the most important one, because this is really what makes the sharding secure. Without that, it's not secure. Like, believe me, it is not. I don't want to release the numbers right now. But if I would release the numbers, your hair would be like, you will lose your hair. The sharding in terms of security without this mechanism is just horrible.
Can we compare that to like sharding in ordinary database systems when we need to ensure that master like
in database system, you have a different consensus mechanism, like Raft, and it ensures the, the eventual like consistency of the and synchronization. So you have a consensus mechanism in database systems, as you know, probably, if it's a clustered database. You cannot live without consensus. But you need to have consensus anyway. Like
yeah. So this component does exactly the same thing as in ordinary database.
Not exactly, because in ordinary database, why like you cannot just use Raft in blockchain? Because in ordinary database you trust every actor, like all the nodes, all the database cluster nodes, you trust them that they will not do something malicious. Here you don't trust, and this is the most important differentiation, right, between the database consensus and this one. So first of all, it's security, and then the second of all is also probabilistic finality, which we can somehow improve down the road, and simply because we can cut certain phases, and we then can lower the thresholds actually. So we can lower the threshold of BFT into 51%. And why is that? So nobody thought about that. So the reason we need a BFT consensus here is forks management, really, right? Because like the fork management is a problem in the designs as a gossip kind of designs, right? And you have a whole, like you need to go arounds to manage forks, and whatever the management you choose, like you allow forks or you don't. In the BFT consensus that we have, we don't allow forks now, but in order to manage forks, and also redundancy in some way, right? Because you kind of, what if the collator didn't produce the block, and then what else? We need to choose the collator. So it's all related to choosing the collator, and then to choosing like the block that need to be that is the right chain, right? But we can because for that 51% is kind of enough, I think, for the management of the forks. And if you lower from 66 to 51, for example, then we lower the finality time of the, like we can create blocks faster.
And why didn't they lower the threshold in original BFT?
Because you break because if you lower the threshold in the original BFT, you break the security, and it stopped working. Again, it's all probabilistic stuff, right? It's all like networking. But the proof in BFT is that only with the 66% consensus, you kind of can can ensure that it works. With the, of course, a lot of messages you send and a lot of rounds that you go. But here, because we have an added security, like we don't need to worry about corruption in shard in the thread so much, because like if the malicious parties, if there is like a lot of malicious parties in the thread, and then they will validate, they need to validate something malicious, and that's something that they need to validate is a block that someone need to collate. So there should be a malicious collator who will collate the malicious block, because without that, obviously there could not be any malicious transaction. But once collator has collated the block, the malicious block, it cannot just feed it to validators anymore of this thread. You also will need to send it to the blockchain, to all the other workchain nodes, and to be and there, then the verification comes into play, and then the whole probability of having a malicious verifier is very close to zero, like extremely close to zero. And in which case, by the way, this part of the design is quite actually, it's somewhat similar to Ethereum 2.0. If you think about that, like they have a different consensus mechanism, but in terms of like, they do have, you know, the verification mechanism, and stateless clients and all that shit. But of course, not that elegant, I think. So you have to consider like two parts. So one part is this verification. You need to kind of take some random function, and you need to calculate on that like modulus calculation of who is the verifiers, who are the verifiers. But then you need a second part of that, is that retrospectively, yeah. You will need to prove like when the verifier compute, like you understand that verifier compute who is the verifier using his own private key. Therefore, only the verifier knows at this particular moment that he or she is chosen as a verifier, right? So that's the beauty of the scheme. Like you calculate, every node calculates, and then some nodes will realize, okay, I'm the verifier. I will verify that block now. And I verify it, and then I send, you know, ACK or NACK to the master chain, right? But then there is an attack, a possible attack, and that's part of the contest. Like I wrote there, you need to calculate, like you need to describe the possible attacks. So I'm just giving you some hints here. So the possible attack, or maybe you will find something else, right? And that's the whole purpose. So, so one of the possible attacks is a lazy verifier. Like I won't verify anything, I don't fucking care, because I'm not getting additional payments for that. Well, so you need to create a mechanism where the post factum, it will be possible to post factum calculate who the verifier should have been around the go, and then look at the master block and see if the verification from that particular node is there, whatever is ACK or NACK. And if it's not there, then we can slash him. So the scheme must be this. Again, you calculate on random number with your private key, and only you can know if you're a verifier or not. But post factum, after blocks or several blocks, any witness will have to be able to calculate if you should have been verified. All right. So so this is like, I need to emphasize that part also. It's important. And the broadcast protection. So this is really more or less it. And then of course the broadcast protection is, okay, let's talk about broadcast protection. So how broadcast protection works. Well, you can make several like, you can just, you know, you can just collect signatures basically, right? If you collect, because you know, like remember that, you know, going to this verification of this block, you know what the validator set. So you know all the validators pub keys and ADNL addresses, whatever. So you can actually like just collect the 51% of signatures of this on the block, on the broadcast of all the nodes. But of course, then that's why I put in the requirements that the timings and you know, delays and everything should be taken into account. Because if you start just doing very naive implementation of that, you will see that it, and of course the messages that you send, like the traffic. Then if you do just naive implementation of that, you just take, 25519 and just do signatures on AdWords, and then you count this, then you will see that you increase the traffic tremendously for every block, and then you also increase the time frame, because you need to wait. Someone need to wait until all the signatures arrives, the 51% of signature arrives, and then only then I can send an attestation. Okay, then we have this somehow proofs of the attestation of 51%, right? So that will be enormous traffic, and it will take a lot of time. It is possible to do, actually, just naive. Yeah, it is possible, but you need to think about traffic. So, and what is hinted in the white paper is that let's use the BLS signatures proposed by Dan Bonnet. And the beauty of BLS signatures is that it is a constant size proof of the unlimited amount of aggregated signatures. So you send, well, in theory, it's 32 bytes. It's not really true. It's not 32 bytes in implementation, but it's close to that. So let's say it's 48, 96, doesn't matter. It's still constant number, and it's not that big. You can aggregate. So then you can create some kind of aggregation scheme where in the nodes, receiving these BLS signatures, aggregate the BLS signatures that they receive, send it further, and then someone has 51% of them, of the signatures, but it's all the constant size, that the messages are the constant size. And if you're broadcasting such things, then within 2 hops, 3 hops, depends on the size of the hop, on the function of the broadcast, then you kind of, on the 3 hops, you can get 51% signatures aggregated some nodes, and then the node can send to master chain this BLS. And also master chain does not get bombarded with the huge lists of the signatures. It only receives, whatever, 90 bytes or 100 bytes. And because the master chain nodes knows all the public keys of all the validators, it can verify that this 100 bytes actually contains all the signatures of the 51 validators from the set. Now, what I said is sounds very magical and simple. It's not that simple, actually, and that's what we wanted. Well, actually, I thought about getting a BLS, in particular, taking the BLS part of that contest and actually make separate contest in the cryptography group for the BLS, because there is some tricky stuff in that. There are some attacks on BLS that need to be taken into consideration. So my thought in that respect, in this contest, that the BLS part won't be, that may not be that, we can exclude BLS in-depth research from this part. Let's assume, if you choose BLS, or you may propose something else, but if you choose BLS, let's just assume that make just basic research on BLS would be fine here. So you don't need to go into cryptography and understand, what they attack and how to protect against this attack or that attack. There are several attacks on BLS potentially, and we will run that. So if you what you do need to concern about is the the time frame it will take to create BLS signatures, the traffic in general, and the whole scheme about how this whole BLS structure will be organized. Okay, so and then I will make a separate proposal for BLS research in the cryptography group, because maybe there is stuff that we don't know. Of course, our cryptographers did a research for the last 2 months on the BLS, and of course a lot of stuff was found, and we know something about them, but maybe not everything. So we will probably make another contest on the BLS signatures in the cryptography group. It's a quite new stuff, so as anything new in cryptography, it's, you know, but by itself, it's kind of, you know, might be a problem. So need to be researched. But BLS is used in ETH2.0 as well. But I think there are problems with their use case as well. Like they told me that they choose like different what's it called, curve, which is maybe not secure. So but anyway, that doesn't matter. It doesn't concern us. What is concerning us is that we need to choose everything, which is fine, and as long as we win well in the current state of, you know, of the art. Well, that's it. I mean what I kind of expected from this is as detailed as possible technical description of that, like basically extending that to the technical description, and with thoughts about potential attacks on that realization. Of course, you need to make some research of what kind of third-party libraries to use in your design. Like it should be feasible and it should be, you know, of course, integrated into the node. So you need to also kind of describe how it will be integrated into the node, current Rust node. Yeah, so you need to get familiar with the Rust node and how it works, at least some portions of that, some parts of that. And then you know, and if you can simulate, then of course, you know, you can simulate, and that would be a plus, obviously. That's it.
So do I understand well that one possible attack you mentioned is lazy verifiers, and the second and the very second possible attack is choosing 51% of kind of verifiers, like so choosing malicious nodes as verifiers, and all malicious nodes. If all malicious nodes is chosen as verifiers, only then will you have the proofs, and only then you have a successful attack.
Well, the thing is that you don't know. I mean, in design, you don't supposed to know who the verifiers will be until you actually produce the block, and so you cannot mine, and that's very important, that you cannot mine the block. You shouldn't be able to mine the block for the potential verifiers, for the controlled by you. All right, so that's the idea, is that you cannot mine in this architecture, in this implementation. You shouldn't be able to mine the block, because the malicious verifier can do whatever he wants. I mean, he can create the block, change something in the block all the time until it mines, you know, whatever hash of the block, and so on. So that should be mitigated as well. Like, and it's described basically here that it doesn't work. Like, you cannot mine, because you will never be able to assume that you control all the verifiers, because the number of verifiers is undeterministic. So you cannot assume that even if you control 50% of the network, you cannot assume that you control all the verifiers. In fact, like even if you control more than that, you cannot assume. But if you control more than that, then the question, is it you who is producing malicious block or the other part? So that's why we consider always 50%. Like 51. Like we never consider more than 51 protection, because it doesn't make any sense. Like, you don't need to protect more than 51%, because if you're protecting for more than 51%, that you are the attacker then, or you may be the attacker.
Seems fair.
Well, that's it. I'm done. I don't know, Alex.
Any questions?
Yeah.
Actually, because I'm not ready to go through the document and immediately discuss it. I need some time to think about it. I'm I'm a bad blitz player.
Okay, a rapid maybe. Like this call is more like a rapid game, turning into classical very quickly. Anyway, yeah. So anyway, this is the proposal. Like I didn't like the numbers there in terms of 2 weeks and 200,000. It's all like my fantasy. I don't know. It's doesn't really matter. I don't care. I do think that we need to start as soon as possible, simply because we have a very tight schedule for the rest of the things that we need to do. And I am already like, I will present the ramp kind of description for the contest next week. And let's move on, because like, let's move, because like we really need this, you know, and it's not really, like we, of course, we have an internal schedule for these implementations, but I want to prepare some developers to be able to kind of verify, look into what is written, so we're not alone looking into all this stuff. And the incentive here is not like, you may not like win the contest, but at least if you participate, then you will gain some knowledge which will allow you to kind of look at into the next stages contest and into the final code that will end up in the node, and understand what is it there, and be able to kind of you know, judge and comment and, you know, find bugs or whatever. So I think that generally we're looking into involving more people into general kind of development of the protocol, even if your particular code will not end up in the node by the end. It doesn't really matter, because that's not the goal. The goal is not to write the node. I mean, we will write the node. It's not the problem. The problem is that to get more people involved into the protocol development.
Okay, but by the way, I don't see neither Sergey Yegorov nor Michael Komarov here, so
well, they can watch. They can watch. Yeah, they can watch.
Yeah,
later. It's not a problem.
Yeah, I'm just assuming that you will be, Ton Labs will be the only participant here.
Oh, no, I don't think so. I think that's whoever made the current contest submission for the node participation, I hope they will participate. Like Stefan is here. So I don't know, Stefan, are you going to participate?
Steven?
Oh, I'm sorry. Can you repeat the question, please?
I'm just asking, are you going to participate? Your team.
So I can speak for the other ones, of course, but personally, I'm not, I don't think I will be part of this. This.
Because Olap's did submit, you know, their.
Yes, for the
node.
Yeah, for the node. So that's why I can't say if they are going to participate. I think so, because they are starting to gather a team to work on, but I'm not particularly involved in it.
Okay, understood. But yeah, what I'm saying is like the Olaps and Provenda, at least they're, I'm sure, going to participate. So they submitted the, you know, the contest, and we're definitely, you know, looking forward for that. I don't know if Michael will participate with Neil Foundation, but nevertheless, because they participate in the cryptography group, and I think maybe in the formal verification, I'm not sure, but nevertheless, the whole this protocols will going to like, because now the formal verification SubGov is actually started kind of the process of verification of the node, but the goal, as they stated, to verify the node in the end. So like formally verified nodes, I don't know if it's feasible, but nevertheless doesn't matter, even if it would be just, the specifications that will be formally verified, or like the simulations that will be formally verified. It's also fine, and the thorough audit of the code anyway, it's very like beneficial and welcoming stuff. So yeah, I mean, nevertheless, like they will participate, and even if they not going to win, but they will be using this in the formal verification then of the nodes, and a review of the code. So it's good stuff. Anyway.
So let's take a week for read the document. Let's give guys time to listen the recording. It will be available in several hours, and let's give them possibility to ask questions, make some proposals, discuss this, and like next Thursday, if we will have some questions or issues, we could discuss it next Thursday and run second test after this, or if everything will be clear. And so anyway, we could start it on next Thursday. Right?
Yeah, let's do that. Sure, that's fine.
Okay. Anybody else has any questions, ideas, thoughts, proposals? Ivan? Okay, then let's make a countdown. 5, 4, 3, 2, 1, 0. So thank you, everybody. Thanks, Mitya, for explaining this. And let's meet in a week then.
Yep.
Okay, fine.
Fine. Bye.
Bye, everyone, and thank you again for switching in English
Okay.
during your meeting. Really appreciate it.
Fine. Okay.
All right. Thanks. Bye-bye.
Bye.
Thank you. Bye.